In this presentation, we will be presenting on market survey, ammonia plant site selection, ammonia production process, our process plant creation, and also our overall expected mass balance and our proposed and plant site PFD. Okay, so we choose ammonia as our product based on our market survey, where there will be an increasing demand for world ammonia demand, which is expected to increase on 2030 with 209.4 million metric ton. Also, the non-fertilizer use of ammonia will be increasing towards 2030 with 55.3 million metric ton. And also, it's expected that it will be increase of compound annual growth rate of 7.28% by 2025. And we also chose ammonia as our product due to our local yearly ammonia production, which is around 2.54 million tons per year, which is around 1.5% total ammonia world demand. So we can see the potential of building another ammonia production plant in Malaysia. Okay, we choose to build our ammonia production plant on Gebeng Industrial Estate, which is situated in Pahang, due to the attractive incentives and initiative by Pahang State Government to promote Pahang as one of the biggest industrial hub in Malaysia. Also, there are no direct ammonia process plant competitors around the area, so it can help our distribution of ammonia locally. Also, there are low and competitive utility tariff, which is a low water tariff by Pengurusan Air Pahang Berhad, so it can help on our production cost and also increase our production profit. Also, in this area, there is development of Malaysia-China Kuantan Industrial Park, MCK, with conjunction of China, which can help our ammonia export to China and also to the world ammonia demand.
Hi, I am Shuaina Shafi. So now we are going to proceed about reaction pathway to produce ammonia. Basically, reaction pathway that we propose is Haber-Bosch process, thermochemical cycle process, and direct synthesis of catalytic reduction of nitric oxide with hydrogen addition of carbon monoxide. But for our project, we choose a Haber-Bosch process, and I will explain furthermore why we choose that process. Haber-Bosch process is an artificial fixation process. The process converts atmospheric nitrogen to ammonia by reaction with hydrogen using a metal catalyst under high temperature and pressure. The method for producing hydrogen from hydrocarbons is known as steam reforming. To produce the desired end product ammonia, the hydrogen is then catalytically reacted with nitrogen, which is derived from processed air, to form anhydrous liquid ammonia. So this step is known as the ammonia synthesis loop, also referred to as Haber-Bosch process. Here is the reaction: 3 hydrogen plus nitrogen to produce 2 mole of ammonia. Due to the nature of the catalyst used in the ammonia synthesis reaction, only very low levels of oxygen containing, especially carbon monoxide, carbon dioxide and water compound can be tolerated in the synthesis, which is hydrogen and nitrogen mixture gases. Relatively pure nitrogen can be obtained by air separation, but additional oxygen removal may be required. As you can see here, here is the reaction path for overall reaction path for Haber-Bosch process, and the gross profit value is 0.669 USD per kilo ammonia. As you can see, here is the comparison table for weightage for reaction pathway 1, which is Haber-Bosch process. Reaction pathway 2 is thermochemical cycle process, and another one is reaction pathway 3. As you can see, for gross profit, the weightage is 40%, conversion selectivity 25%, temperature 15%, and produced by product is 20%. For gross profit, the score for reaction pathway 1 is the highest, which is 5, and the mark is 2, compared to reaction pathway 2, 1.6, and reaction pathway 3, 0.4. After we calculate, the gross profit for reaction pathway 2 is 0.471 and reaction pathway 3 is negative 4.781, which is lower than reaction pathway 1. So the table clearly shows the first reaction pathway, which is Haber-Bosch process, is the best because it has highest value compared to others by considering the gross profit, selectivity, temperature and recycle component. So this process is the most economical for fixation of nitrogen since it used as the main industrial procedure for the production of ammonia today.
Okay, I am Farah Samarigazi will presenting on first and second step of K synthesis. First step is eliminating differences in molecular depth. Here, three reaction pathways are proposed, which are Haber-Bosch process, thermochemical cycle process, and direct synthesis. And we choose the Haber-Bosch reaction because it has the highest total score compared to other pathways reactions. Now we move to second step, which is distribute chemical matching source and sinks. In this step, there are some processes which are desulfurizer and primary reformer, secondary reformer, and carbon monoxide sieve converter, methanol, and ammonia converter. Desulfuration is a process carried out to remove sulfur from a material which in this case is found in natural gas feeds. The primary reformer functions to produce hydrogen gas from reaction between natural gas and steam in a radiant tube containing a nickel catalyst. In the secondary reformer, air is added to the gas reaction process. Nitrogen from the air is used for the production of ammonia and oxygen from reaction above to provide the heat needed for the reforming reaction. And sieve converter is used to reduce the carbon monoxide content, which can interfere the reaction in the ammonia converter and convert it to carbon dioxide. For methanol, the content of carbon monoxide and carbon dioxide that escape from the absorber can be toxic to the Fe catalyst in the ammonia converter. So the content must be removed by converting it to methane using a nickel catalyst. And then the synthesis gas is then heated and sent to the ammonia converter, which nitrogen and hydrogen are reacted to form ammonia with the ammonia converter.
Assalamualaikum and very good morning. My name is Nur Aihanisa and I will present the next case synthesis, which is differences in composition. First, we need to remove CO2 because CO2 is toxic to the catalyst inside the ammonia converter. Next, we also need to remove water because water can freeze and clog the pipe flow during the refrigeration system. So we need to put a dryer inside our ammonia production system. Next is a purifier because we need to purify the gas stream to minimize the gas impurities and to reduce the compressor load. To separate ammonia as our product, we need to put a refrigerant system, and the gas from refrigerant system will enter the push gas recovery unit where the gas will push or recycle back to the system. So part case synthesis, which is eliminate differences in temperature, pressure and phase. This flowsheet diagram with temperature, pressure and phase change. Next case synthesis, which is task integration, where we assign equipment to each temperature, pressure and phase change. This is a flowsheet diagram where we assign the equipment according to pressure, temperature and phase change. Balance, we decided the production capacity is 600,000 ton per year of ammonia, and from the overall equation we can get mass flow rate of methane and nitrogen. Is overall process flow diagram for ammonia production. That's all from us. Thank you.